In previous modules in this series, we've looked at typical boiler construction, including combustion equipment for different types of fuel. So let's turn our attention now to boiler operation, and we'll begin by looking at a typical startup procedure. Of course, the precise actions and maneuvers that you take will vary from boiler to boiler, particularly with different types of firing. But the principles and operating requirements are the same. Let's assume that our boiler is being returned to service after a maintenance outage. It is completely cold. The first step in preparing this boiler for service is to make sure that all of the maintenance jobs have actually been completed and that all permits to work have been canceled. We then need to take a walk around the boiler to make sure that all workers are out, all tools, materials, and debris have been removed, and that access doors and manholes are closed. All auxiliary equipment, such as feedwater pumps and fans, must also be ready for operation with switchgear and breakers racked in and power supply available. If the boiler has been drained during maintenance, it will now be necessary to refill to the working level. Before admitting any feedwater into the boiler, make sure that the appropriate drain valves are closed. We must also check that the air vent valves are open on top of the steam drum. The superheater drain valves should also be open. In order to pump feed water into the boiler, it may be necessary to run the feed pump. However, in many installations, an auxiliary low-pressure pump may be provided for this purpose. As feed water enters the boiler and the water level rises in the tubes, air will be expelled from the open vents. The boiler should be filled to a level so that it is just visible in the bottom of the gauge glass. That is about 3 or 4 inches, say 10 centimeters below normal working level. The reason for this is to allow for expansion as heating of the water takes place. While the boiler is filling, we should make sure that the combustion equipment is primed and ready for service. Startup burners normally use light oil or gas, both of which are readily combustible. However, before lighting a fire in the boiler, it is essential to purge the furnace and gas passages. This action consists of passing a large quantity of air, say 40% of rated flow, right through the boiler and up the chimney to atmosphere. The objective of this is to purge, that is, sweep away any combustible gas that may be present, perhaps in pockets of the furnace, superheater, or air heater. If purging is not carried out, there is always the potential for an explosion to occur when the first burner is ignited. The purge action is carried on for several minutes, and this requires that the forced draft fans be run and induced draft fans if installed. After purging, the airflow is reduced to the pre-established startup value, usually 10 or 15% of rated flow. The boiler is now ready to begin firing. Each startup igniter is initiated either by local push button or remotely from the control room. The igniter runs through its own startup sequence as follows. Check that there is a flow of combustion air. Check that oil pressure is correct. Close the switch to ignite the spark plug. Check that the arc is present. Open the ignition fuel valve. Observe that ignition takes place and that the fuel continues to burn. Once the fire is established, the spark plug igniter will be switched off by a timer. If ignition does not occur within about 30 seconds, the fuel valve will be closed and the condition alarmed. The rate of adding heat to the boiler is dependent upon the number of startup guns which are placed in service. Also, in many cases, the fuel pressure to the startup guns can be adjusted so as to allow further control over heat input to the boiler. It takes a considerable amount of time to heat all the metal in a cold boiler, including the water contained inside the tubes and drum. We should expect to see steam blowing from the air vents after an hour or so. We will also notice that the level of water has risen. This is due to both thermal expansion and also some swell as boiling starts to take place. You will remember we discussed swell and shrink caused by steam bubbles in an earlier module. When the steam pressure rises to, say, 20 psig or 140 kilopascals, the air vents on the steam drum should be closed. At this point, we can assume that all air has been expelled from the boiler, and steam at this very low pressure fills the space above the water as well as inside the superheater as far as the boiler stop valve. The temperature of the water and the steam and the water wall tube metal will all be at or close to the saturation temperature corresponding to the pressure. That is about 230 degrees Fahrenheit or 110 degrees Celsius. This rise in temperature from a cold start will cause a considerable expansion of the boiler metal, and this must be allowed for in the construction of the boiler. For example, this particular boiler, which is bottom supported, is built so as to allow expansion in an upward direction. On large boilers, support is effected from above like this. The boiler is actually suspended and held by these heavy steel rods. In this case, expansion takes place in a downward direction. In some installations, you may find an indicator which shows the amount of expansion from the cold position. This may be as much as 12 inches or more, say 30 centimeters, between the cold start position and full load. Because of the stresses imposed by this expansion of the body of the boiler, there is a limit to how fast we can add heat. A general rule of thumb is that the temperature of the water walls should not increase at a rate above 100 degrees Fahrenheit per hour, say 55 degrees Celsius per hour. But during this startup operation, how do we know the precise temperature of the water walls? Well, we can easily infer this from the steam pressure. First, assume that the metal temperature is equal to or similar to the temperature of water inside the tubes. And this will be approximately equal to the saturation temperature corresponding to the steam pressure. Using this information, we can draw a pressure-raising curve based on the 100 degree Fahrenheit per hour limitation. You can see from this curve that initially pressure must be raised quite slowly. However, as pressure increases, then the rate of pressure raising can also be increased. Even so, it will take about 5 hours to bring a cold boiler up to 1200 psia. So bearing this in mind, let's return to our startup procedure. Now that the drum air vents are closed, the steam pressure will start to increase. We should observe that it rises in accordance with our startup curve, but what control do we have over this? Well, if pressure rises too quickly, then we will need to reduce the fuel pressure to the igniters or perhaps extinguish one gun. On the other hand, if pressure rises too slowly, we may need to throttle in the superheater drains, but we cannot go far with this. Remember that it is essential to keep steam flowing through the superheater in order to keep the metal temperature cool. For some period of time, the water level will continue to rise as pressure increases. This is due to increasing temperature plus increase in steam generation, which creates more bubbles in the water. But where is the generated steam going? Well, the only steam flow from the boiler is that passing through the superheater drains. But of course, as the pressure increases, so will the steam flow increase through these valves. Eventually, this flow will become so great that the water level starts to fall. This means we are dumping more steam than is being generated at this time. Eventually, as the water level falls further, it will be necessary to start the boiler feed pump and add feed water. We also may be able to throttle in the superheater drains further so as to reduce this wastage. Actually, the opening of these valves has some influence on the steam temperature at the superheater outlet. How is this? Well, if the steam flow through the superheater is increased by increased opening of drain valves, then the rate of firing will need to be increased so as to continue pressure raising. This results in a greater volume of combustion gas passing over the superheater, consequently transferring more heat to the steam, so raising its temperature. This maneuver is sometimes employed when we are trying to match steam temperature to the steam turbine metal temperature during a unit hot startup. However, remember that in order to achieve this, we are burning more fuel and dumping heat to waste. In some circumstances, this waste heat may be recovered, and we'll be talking more about this arrangement when we discuss turbines in another module in this series. At that time, we will also discuss the procedure for charging the main steam line and opening the boiler stop valve. We must point out here that a boiler stop valve is not always installed. And in this case, the steam line will be charged with steam throughout the startup, right down to the turbine stop valve. Often on a cold start, steam is admitted to the turbine quite early in the pressure raising cycle, say when the boiler pressure is about 400 psi. The objective is to raise steam pressure and temperature on the boiler and run up the turbine at the same time. If this is a reheat unit, the reheat drains must be opened during the run-up period. Once the turbine is synchronized and carrying load, the superheater and reheater drains may be closed, as steam is now flowing through the superheater and reheater and on through the turbine. Also, during the initial loading, it is likely that one or two of the main fuel burners will be placed in service, and the associated startup burners shut down. We are speaking here of heavy oil or gas firing. Where pulverized coal firing is involved, the boiler will usually remain on oil firing until turbine minimum load is established, say 10%. During pressure raising on the boiler, attention must be paid to maintaining the correct water level in the drum. As soon as possible, the automatic water level control should be placed in service. Similarly, other controls should be put in automatic service, although this may not be possible until the turbine minimum load has been reached. We'll be discussing monitoring and control systems in detail later. So at this point, we have the boiler up to rated pressure supplying steam to the turbine generator. The boiler must now be controlled so as to maintain rated steam pressure and temperature as the generator load and consequently steam demand changes. We'll be talking about on-load operation in the next segment, but first, let's take a brief look at a boiler shutdown procedure. As load is reduced on the turbine generator by reducing steam flow, heat input to the boiler must be reduced. This is done by taking burners or pulverizers out of service and reducing combustion air accordingly. Once the generator is taken offline and the turbine stop valve closed, the fire should be extinguished completely. The FD and ID fans will be shut down and dampers closed. All drains should remain closed and feed water topped up to a high level in the gauge glass. In this situation, the boiler is said to be in a boxed up or bottled up condition. As the heat is retained inside the boiler with very little heat lost to atmosphere, the steam pressure will fall slowly, perhaps to 50% within 24 hours. As the pressure and temperature fall, the water level in the steam drum also falls slowly, so that it becomes necessary to top this up from time to time. The objective of this boxed-up condition is to keep the boiler available for a quick startup. In this condition, we can restart the boiler and raise pressure to rated value within, say, 1.5 hours. A different situation would prevail if the boiler was being taken out of service for maintenance. In this case, we would run the ID and FD fans so as to purge the boiler of gas and also to force cool the hot metal and refractory. Even when the pressure falls to zero, further cooling would still be necessary for some time after, so as to allow personnel to enter the boiler. Well, now at this time, let's take a break, and then we'll come back and look at on-load operating conditions. For now, please switch off the tape and review this material in your workbook. Let's now examine the requirements for on-load operation of the boiler and some of the difficulties which may be encountered. The prime task of the boiler operator is to assure that the boiler follows changes in steam demand from the turbine generator and maintains the rated steam pressure and temperature. Steam pressure is controlled by adjusting the heat input, that is, the quantity of fuel supply and associated combustion air. Of course, this sounds easy, but in practice it takes considerable effort and experience to obtain good, clean, efficient combustion. We already know that for efficient operation, a precise quantity of air must be provided to match the fuel input. This curve shows the effect of either insufficient or too much excess air. You can see that with insufficient air, boiler losses increase considerably due to incomplete combustion, with the resultant presence of carbon monoxide and unburned carbon in the flue gas. Increasing the air supply will usually complete the burning of carbon monoxide to form carbon dioxide. It should also reduce the amount of unburned carbon. However, if too much excess air is provided, the heat loss increases again due to the larger quantity of excess gas discharging from the chimney. So this task of maintaining the correct fuel-air ratio is extremely important. The operator must also look at other factors in order to create the very best conditions for combustion. And these factors include physical condition of the burners. Is the fuel and air being directed into the correct location and mixed thoroughly? Fuel atomization in the case of oil, and adequate grinding in the case of pulverized coal. Correct distribution of combustion air between burners and between primary, secondary, and over-fire air. Consistency in fuel quality. This last item can easily be forgotten. It is important that where fuel supply has changed, perhaps from one coal to another, the operator be made aware of this fact and also the characteristics of the new supply. For example, the incoming coal may have a higher moisture content or may be less volatile and therefore more difficult to ignite. It may contain increased quantities of ash, and the ash may be such as to cause slagging. Operators must be aware of these conditions so that they can be prepared for potential problems. Actually, the incidence of boiler fouling and slagging due to ash is one of the major problems encountered in boiler operation. Let's take a closer look at this. The term ash is the generic name given to mineral elements in the fuel which are non-combustible. Typically, the ash is made up of such minerals as silica, alumina, iron, calcium, manganese, and so on. Let's first examine the effects of ash in an oil-fired boiler. We have already noted that fuel oil contains only a small amount of ash, say 0.5%, but this still creates problems. When the fuel enters the furnace, the carbon and hydrogen begin to burn, releasing the metallic elements. Initially, the high flame temperature causes some of these elements to become molten, that is, semi-liquid. However, these particles soon cool as they move away from the center of the flame and consequently solidify and fall by gravity to the bottom of the furnace. The ash at the bottom of the furnace accumulates, often to a thickness of several feet, and eventually the boiler must be taken out of service for cleaning. The time period between outages for cleaning may be 6 months or even as long as 12 months in some cases. The ash deposit is extremely hard and considerable physical effort, assisted by jackhammers, is required to remove the deposits. However, not all of the ash is collected at the bottom of the furnace. Some of the lighter particles are carried in the gas stream through the superheater. If the ash particles are still in a friable condition, they may stick and deposit on superheater tubes and water wall tubes. However, in most cases, the ash deposits are more likely to be in the form of dust, known as fly ash. Where this does collect on superheater tubes, it will result in a reduction in heat transfer and consequently lower steam temperature. Retractable soot blowers are installed, and these are operated usually once per shift to blow the fly ash off the superheater tubes. The fly ash is collected in hoppers below the superheater. The total quantity of ash is quite small, so there is no need to empty these hoppers except at long intervals, such as during the outage for boiler cleaning. A small quantity of fly ash may continue on with the combustion gas to deposit on the surface of the air heater. If this deposit builds up, it may be necessary to take the boiler out of service in order to wash the air heater. To perform this task, jets of water are sprayed onto the rotating air heater to remove any deposits. In the fuel oil-fired boiler, the ingredients of ash which cause the most problem are sodium and vanadium. In fact, the fuel oil analysis usually quotes the sodium and vanadium content in terms of parts per million, ppm. A vanadium content of 250 ppm is considered high and will be troublesome. Similarly, a sodium content over 200 ppm creates problems. Sodium has the effect of aggravating the tendency of deposits to stick on boiler tubes. Vanadium causes high-temperature corrosion in the superheater zone. At the high gas temperatures encountered in this zone, the vanadium becomes molten and mixes with excess oxygen to form vanadium pentoxide, indicated by the symbol V2O5. This molten compound runs down the superheater tubes and forms a hard deposit around the tubes. Worse yet, it causes external corrosion of the tube metal and also of the tube supports. Is there any way that we can reduce the negative effect of vanadium? Well, yes. One way to reduce the formation of vanadium pentoxide is to reduce the amount of excess oxygen which is available for combustion. But this is something of a trade-off. As we know, if we reduce the excess air too much, we run the risk of causing incomplete combustion. Clearly, extremely tight control over excess air is required. In some oil-fired boilers, a magnesium oxide additive is mixed with the fuel. Its objective is to raise the fusion temperature of the vanadium pentoxide, and so hopefully allow it to pass right through the superheater zone without settling on the tubes. So much for ash in fuel oil. Where processed natural gas is used as the fuel, we are extremely lucky, as it contains zero or negligible quantities of ash. Let's now turn our attention to coal, which unfortunately does contain large quantities of ash, typically 12 to 15%, and in some cases much higher. In all cases, when burning coal, the boiler must be designed for a specific coal. For instance, where a large quantity of ash is contained in the fuel, the volume of the furnace must be large in order to handle the large volume of material. With pulverized coal firing, the fouling mechanism is similar to that for fuel oil. That is, the metallic elements are released during combustion and fall to the bottom of the furnace. This is known as bottom ash. Clearly, the amount of ash which is collected at the bottom of the furnace is far greater than in the case of the fuel oil boiler. For this reason, ash must be removed on a continuous basis, or at least daily. The bottom of the furnace is shaped like this so as to allow ash to run down the water-cooled slopes and fall into the ash pit. From here, various means are provided for removing the ash. Water is used to break the ash into manageable components. In one typical system, a drag scraper pulls the ash from the ash pit into a crusher, where the large pieces of slag are broken down into smaller pieces. From the crusher, the ash may be conveyed to a processing plant for recovery as construction fill. Another method uses high-pressure water to flush and carry the ash to the ash dump, which is in the form of a pond. Some of the water is then recirculated to repeat the process. Actually, only 40 to 50% of the ash forms bottom ash. The remainder, as fly ash, passes on through the boiler to be removed from the hoppers of dust removal equipment, such as the precipitator. The fly ash system actually works under vacuum that sucks the fine dust out of the hoppers and conveys it to the storage silo for eventual disposal. Because of the relatively large quantity involved, fly ash from coal can cause serious problems due to deposits, fouling, and blockage of gas passes between superheater tubes. One serious problem is the formation of deposits on the furnace water walls, resulting in loss of heat transfer to the water inside the tubes. This means that the boiler needs to be fired harder in order to maintain output. The consequence of this is that the temperature of combustion gas entering the superheater zone is higher than normal, causing the steam temperature to rise. Hopefully, we can provide enough de-superheating water to keep this under control. But a greater problem is that the higher gas temperature may be sufficient to bring certain elements of the ash into a molten state, forming large clumps of slag that can block the flow of gas through the superheater and reheater tube banks. Apart from visual inspection, this condition can be confirmed by looking at the draft pressure indications at different points in the boiler. In order to help maintain clean furnace walls, a large number of rotary soot blowers are installed on the walls, in addition to the retractable blowers that are provided to keep the superheater and reheater tubes clean. In many plants, it may be necessary to operate all or at least some of the soot blowers on every shift. This operation is usually performed remotely from a panel in the control room. We've already mentioned that sulfur contained in the fuel can cause serious corrosion problems. This occurs because the sulfur gases SO2 and SO3, when mixed with water, may be converted into H2SO4, sulfuric acid. But where can the water come from? Well, you'll remember that the combustion of hydrogen in the fuel produces water, or water vapor to be precise. Now, as long as the temperature in the gas passing through the boiler remains high enough, this water remains as vapor and consequently does not mix with the sulfur gases to form sulfuric acid. However, if the temperature of the combustion gas is allowed to fall below what is known as the dew point, about 250 degrees Fahrenheit, that is 120 degrees Celsius, sulfuric acid may form and cause considerable damage to iron and steel components. The area where this is most likely to occur is in the air heater. Remember that the incoming air is entering from atmosphere, and this may be at a temperature of, say, 60 degrees. Consequently, the temperature of the metallic element of the air heater in contact with the incoming air will also be quite low. In order to avoid air heater corrosion, we need to make sure that the temperature of the combustion gas leaving the air heater is above about 350 degrees Fahrenheit. The precise safe temperature depends upon the actual fuel analysis. But how can we control this exit gas temperature? Well, the most commonly used method is to preheat the air entering the air heater by passing this through a steam preheater in the ductwork. This is controlled so as to raise the air temperature to about 150 degrees Fahrenheit. On many installations, this preheater is only used during low load operating conditions. At high load, the gas temperature leaving the boiler is high enough for the metal temperature to remain above the dew point in the air heater. By raising the exit gas temperature, we do incur a penalty, That is a loss of efficiency because the waste gas is now discharging to atmosphere at a higher temperature and consequently a higher heat loss. Like many segments of operation, we are faced with a trade-off. Either lose boiler efficiency, which means increased fuel consumption, or suffer damaged air heater components, which will result in replacement cost and outage time. Clearly, there is an efficiency advantage when burning low sulfur fuels. Many gas-fired boilers run with exit gas temperature as low as 270 degrees Fahrenheit, 130 degrees Celsius. We briefly mentioned the effect of boiler fouling and slagging on steam temperature. Other than soot blowing, do we have any other means of controlling steam temperature? Well, yes, we do. You will remember that we discussed in an earlier module the system of attemperation, where desuperheating water is injected into the steam between the primary and secondary superheater. A similar installation is fitted to the reheater so as to control reheat temperature. However, in both of these cases, attemperation is in one direction only, to prevent temperature rise. If all of the desuperheater water is shut off, what can we do to increase steam temperature? Well, one way of achieving this is by using upper row burners only where load permits. In this case, the combustion gas entering the superheater will be at a higher temperature as less heat is absorbed in the furnace. A variation on this is to have tilting burners. In this case, we can direct the flame down like this or up like this so as to increase superheat and reheat steam temperature. Yet another way to increase steam temperature, sometimes used on small boilers, is to increase the amount of excess air supplied for combustion. The effect of this is to increase the volume of gas passing through the furnace, which in turn absorbs a certain amount of the heat released by combustion of the fuel. The result is that less heat is transferred to the water wall tubes, but more heat is carried over to be transferred to the superheater. Of course, you can see the disadvantage of this method. It is uneconomic, as it increases boiler heat loss. Moreover, this technique may not work with all boilers. It depends very much upon the design of the boiler and the location of superheaters. So up to this point, we've looked at the factors affecting boiler operation. Now, we need to look at the actions required to control the boiler. And we'll talk about this in the next segment. For now, please switch off the tape and review this material in your workbook. In order to make the correct adjustments during boiler operation, we need a continuous flow of information so as to indicate the actual operating conditions. Monitoring equipment is installed at many points on the boiler to measure, indicate, and record the status of different operating parameters. Taking this oil-fired boiler as an example, let's consider which particular points we would like to measure. Or to put it another way, what do we need to know in order to operate the boiler efficiently? We can conveniently split our monitoring requirements into specific areas. The steam and water path, the air and gas path, combustion conditions, fuel supply, equipment status. The most obvious starting point is the steam outlet pressure and temperature. After all, this is what we are producing. It is also necessary to know the output steam flow, usually indicated in pounds per hour, kilograms per hour, or tons per hour. Water flow into the boiler will also be measured, and this in most cases will be approximately the same value as the steam output. Any difference may be accounted for by continuous blowdown from the boiler, which is effected in order to control the chemical condition of the water. This subject will be dealt with in the next module in this series. We also need to know the temperature of the water entering the boiler so that we can check its enthalpy for efficiency calculations. Feed water pressure after the feed water control valve will be virtually the same as pressure in the steam drum. Note that pressure in the drum will always be higher than the steam outlet pressure due to the pressure drop as the steam passes through the superheater. In some units, the pressure and temperature at the primary superheater outlet header may be measured. But more important in this area is the need to know the flow of de-superheating water provided for steam attemperation. This indication can provide useful operating information regarding boiler cleanliness. For example, if we find that a large flow of de-superheating water is required, it is probably an indication that the furnace walls are dirty and need soot blowing. Conversely, if the steam temperature is falling and the de-superheater water flow is zero, we can assume that it is the superheater tubes that are dirty and need soot blowing. So much for the steam and water side. Now, let's move on to look at monitoring of the air and gas circuit. First, temperature. It is general practice to measure temperature at the FD fan inlet, that is, ambient air temperature, the air inlet of the air heater, if fitted, the air outlet of the air heater, gas temperature at the boiler outlet, that is, before the economizer, if fitted, the gas inlet temperature to the air heater, the gas outlet temperature from the air heater. This last temperature reading is very important, as it indicates the temperature of gas exiting from the boiler to atmosphere. The higher this temperature, the greater the heat loss from the boiler. Heat loss will also be affected by the amount of excess air provided. This is indicated by measuring oxygen content in the flue gas. This should be kept as low as possible, providing that carbon monoxide or other combustibles do not form. Thus, another useful measurement in the flue gas is the concentration of carbon monoxide. Typically, an efficient boiler would be run with an indication of, say, 1.5% oxygen and 120 ppm carbon monoxide. Another important parameter that must be measured is the air flow. This refers to total combustion air supplied, primary, secondary, and tertiary where applicable. This measurement of airflow is often used in automatic controls, which ensure that air supply is proportional to fuel. We've looked at temperature readings for the air and gas path, but what about pressure? Certainly the indication of air and gas pressure at different points can be very useful to the operator. Taking our oil-fired boiler as an example, pressure is normally measured at the following locations: the FD fan outlet, the burner wind box, inside the furnace, after the superheater outlet, at the economizer outlet, at the air heater outlet. The actual pressure throughout the draft system is quite low, and therefore a small unit of measurement is used, that is, inches or millimeters of water gauge, indicated as WG. 1-inch water gauge, that is 25.4 millimeters, is equal to a pressure of 0.036 psi, or 0.25 kilopascal. The particular boiler we are studying here is not equipped with ID fans and therefore operates as a pressurized system. In this arrangement, the pressure inside the furnace will typically be about 8 inches water gauge, say 200 millimeters. After a period of continuous operation, this value will tend to rise as the passage between the superheater tubes becomes blocked with ash and slag deposits. The pressure on the FD fan outlet will consequently need to rise, which means that the fan will have to work harder. Eventually, we may come to the point where the fan simply cannot push the required quantity of air through the boiler, resulting in decreased steam output capacity. On a balanced draft system, where ID fans are installed, the situation is different. In this arrangement, the ID fan is controlled so as to maintain within the furnace a slight negative pressure of about ½ an inch water gauge, say 13 millimeters. In this case, as the superheater tubes and/or air heater become blocked, it is the ID fan that will need to work harder to create a greater negative pressure in order to overcome the resistance to flow. Now let's turn our attention to the fuel supply. In the case of fuel oil firing, it is common practice to measure and indicate the following points: fuel oil pressure and temperature, fuel oil viscosity at the burners, fuel oil flow, ignition oil pressure and flow, individual burner gun position and on-off indication. Gas burners need a relatively small amount of instrumentation, typically measuring fuel flow and pressure at the burners. Where pulverized coal is used as the fuel, the following points are usually monitored: the quantity of fuel supplied. This is measured at the weighers which feed coal into the mill. Primary air and secondary air flow. Air pressure or draft through the mill system. Temperature of primary air at the mill. Now, this last item is important. Hot air from the air heater is provided to the mill in order to remove any moisture that may be present. However, it may be necessary to reduce this temperature to prevent fires occurring in the mill, depending upon the type of coal being fired. This is achieved by admitting tempering air from atmosphere to mix with the primary air so as to achieve the desired temperature. In this review of monitoring points, we're concentrating on the major items. Further instrumentation is required for monitoring boiler emissions and other environmental factors. We'll be discussing this in the next module. No doubt on your boiler there are many other monitoring locations. You must learn where all of the sensors are located and the significance of the information provided. Measurements are performed by appropriate pressure, temperature, or flow sensors. At some points, local indication is given, but normally the measured information is transmitted to a central location for display. In the traditional control room, continuous analog readings are indicated on instruments and recorder charts like this. The experienced operator can sweep his eye across the panel and observe all of the operating parameters at a glance. Indicating lights are also available to indicate equipment on and off and valve positions. Nowadays, this system is replaced by a computer terminal with perhaps 2 or 3 CRTs that provide the same information. The computer or microprocessor has the advantage that it can store information, and this can be retrieved where we need to investigate operating incidents. The computer can also print out operating logs at predetermined time intervals, and can also provide a sequence of events printout in case of system upsets. Whether we're using a traditional or modern system, the information from sensing devices can also be used to operate automatic controls. We'll be taking a closer look at boiler control systems in the next module. But at this point, it's time for us to take a break, and then we'll come back and talk about protection devices on the boiler. For now, please switch off the tape and thoroughly review this material in your workbook. When we think about protection of the boiler, we need to consider just what are the hazardous conditions that may arise during boiler operation. What is it that we have to protect against? Well, the basic dangers are a furnace explosion due to incorrect combustion conditions, a rupture of boiler tubes due to overheating, rupture of metallic components due to excessive internal pressure. Now, there are a number of different operating conditions that can lead to the dramatic failures that we have just mentioned. So the boiler must be equipped with first an alarm system to warn the operator of impending dangerous conditions, and secondly, protective devices that will automatically take preventive action. One of the most obvious potential hazards is that of water level control. If for any reason insufficient feed water is supplied to the boiler, then the water level in the drum will fall, and eventually there will be insufficient water to provide circulation. The result would be rapid overheating of water wall tubes and tube rupture in many cases. Even though today's boiler water level control systems are highly reliable, we must still guard against this possibility. Usually, a low water level alarm will enunciate when the level falls to, say, minus 10 inches. That is 250 millimeters below normal operating level. If no action is taken and the level continues to fall, say to minus 20 inches, that is minus 500 millimeters, then the boiler trip relay will be activated. So what does this relay do? Well, its most important action is to shut off the fuel, thus extinguishing the fire and removing the source of heat. The fans are normally left running, but with the airflow through the boiler adjusted to a preset minimum position, say 10% of normal rated airflow. This will clear residual combustion gases out of the boiler and at the same time keep it in a ready state for a quick start. However, if the feed water conditions cannot be recovered, then the operator will shut down the fans and close up the boiler. But what happens to the steam pressure at the boiler's steam outlet? Well, of course, as soon as the fire is extinguished, this pressure will start to fall. So in order to protect the downstream equipment, the boiler trip would also need to shut down the turbine and other downstream equipment. If the boiler happened to be feeding into a common steam header in parallel with other boilers, then the boiler trip would close our boiler stop valve. So much for low water level. But we also run into problems if the water level rises too high in the steam drum. In this case, we run the risk of water being entrained in the steam and passing on through the superheater and on to the steam turbine. Any tiny water droplets contained in steam can cause tremendous damage to turbine blades because of their extremely high velocity. So high water level in the boiler is a potential danger to the steam turbine. Again, a high water level alarm will enunciate, to be followed by a high water level trip. We've just mentioned the potential overheating of boiler tubes due to lack of water. But as we have mentioned before, we can also run into overheating of superheater tubes during startup due to lack of steam circulation through the tubes. It is quite common to monitor the temperature of superheater tube metal, as this provides useful information during startup. In most installations, the superheater tube metal temperature monitor does not trip the boiler, but it does actuate alarms when the temperature rises to an abnormally high level. Now, in addition to problems caused by high temperature, we can also damage boiler tubes and components by excessive high pressure. But what could cause such a rise in steam pressure? Well, just imagine what happens when the boiler suffers a load rejection. That is, the steam turbine or other downstream equipment suddenly decreases load. In this case, the boiler is suddenly left with minimal steam flow output and a large heat input still entering the boiler. The result is an immediate increase in steam pressure. In order to alleviate the immediate pressure rise, safety valves are fitted at different locations, such as the main steam outlet from the boiler, the secondary superheater outlet header, the primary superheater outlet header, the steam drum. The safety valves are calibrated so as to lift in a desired sequence. That is, the outlet valves first and the drum safety valves last. The objective is to make sure that adequate steam flow is maintained through the superheater tubes. Once pressure falls back to normal, the safety valves close again in the opposite sequence, that is, drum first. But how do we correct the high pressure situation? Well, clearly, we need to decrease the fuel input to the boiler. Sometimes the reduction in steam demand is short-lived, and the pressure falls again, just as the operator is reducing fuel input. However, if the load rejection is complete, such as a steam turbine trip, then it may be necessary to shut off the fuel supply completely to the boiler. A master trip button is often provided for this purpose at the control console. Normally, the fans are kept running so as to keep the boiler purged of combustion gases and also to be ready for a quick start if required. The precise calibration of safety valves forms an important part of boiler maintenance, which must be carried out at regular intervals. On many boilers, the safety valve located at the steam outlet is electrically operated and is known as an electromatic safety valve. This has the advantage that the valve can be opened manually by the operator if he wishes to increase steam flow through the superheater during startup, when pressure is far below normal. We've just talked about load rejection causing a steam pressure rise, but this has other effects too. The sudden rise in pressure causes many of the steam bubbles which are contained in the water to collapse, with the result that the boiler water level in the drum falls rapidly. Most control systems are able to cope with this shrink by opening the feed water control valve wide to increase feed water flow. An incidental effect of this large quantity or relatively cool feed water entering the boiler is to help cause the steam pressure to fall back to normal. The reverse condition occurs if we try to pick up load too fast on the turbine. In this case, the steam flow increases rapidly, the pressure falls, and the water level in the boiler rises. Note that this phenomenon of shrink and swell only occurs during very rapid changes in steam demand. Under normal operational variations, the automatic control system is able to cope well and maintain a stable water level. In boiler operation, the most potentially damaging condition is that of a furnace explosion due to a fuel-rich atmosphere. The presence of a large quantity of unburned carbon or carbon monoxide entering into contact with oxygen and then igniting will burn so rapidly as to form an explosion. A typical case may occur during startup. If fuel enters the furnace but for some reason does not ignite, even though we have plenty of combustion air available, we have conditions for an explosion. If we continue to supply more and more fuel and then suddenly provide a source of ignition, a furnace explosion would occur. This explosion can be very violent, causing tubes within the furnace to bend and break, support structures to buckle, and serious mechanical damage through the boiler. For this reason, during startup or at any time, if there is ignition failure, the burner management system will automatically shut down the fuel input. But how does the burner know that ignition has failed? Well, this is achieved by fitting flame detectors on each individual burner. If the flame is extinguished for any reason whatsoever, or even a non-start, the device actuates a trip circuit to close the fuel supply valve to that particular burner. It also annunciates an alarm so that the operator is aware of the condition. Once the burner is tripped, it goes through a purge cycle. This consists of blowing compressed air or steam through the burner so as to clean out any fuel or carbon which may be present inside the burner or at the tip. The word purge is also used in connection with clearing the furnace of any combustible gases which may be present. We have mentioned this before. During startup, a purge relay actually prevents the fuel system from activating until the purge cycle has been complete. That is, the flow of a large quantity of air through the furnace and boiler for several minutes. Actually, the purge relay does not provide any protection for the boiler when the unit is on load. It merely prevents us starting the boiler and providing fuel under potentially dangerous conditions. Let's consider what would happen to the boiler in case of loss of fuel supply. For example, suppose a fuel supply valve on a gas or oil-fired boiler closed due to a control equipment error. Well, in this case, the fire would be extinguished and all of the flame detectors would shut off the fuel supply to their respective burners. This safety action is important because imagine what would happen if the faulty control valve were to suddenly open again after, say, 30 seconds. You can imagine the large quantity of gas or fuel oil entering the furnace with no flame or source of ignition. It would mix with the air to form a highly explosive mixture, which, coming into contact with hot boiler tubes or refractory, could actually cause a tremendous explosion. This potentially hazardous condition is prevented by the closure of individual burner fuel valves by the flame detectors. Additionally, loss of fuel pressure will cause the shutoff valve to close. Let us look at another hypothetically dangerous situation. Suppose the forced draft fan tripped so that we suddenly lost our supply of combustion air. Again, if fuel continued to enter the furnace, we would have a highly explosive mixture that may self-ignite on contact with hot furnace walls. To prevent this possibility, loss of forced draft or tripping of forced draft fans will trip the boiler. That is, it will shut off the fuel supply to the boiler. Another hypothetical condition we need to examine is the loss of induced draft by inadvertent tripping of ID fans. Initially, with forced draft still being supplied, the pressure inside the furnace would rapidly increase from slightly negative up to a relatively high value, say 30 inches, 760 millimeters water gauge. In a very large furnace, this internal pressure may be sufficient to cause the water walls to bow outwards, with possible damage to the supporting structure. Protection against this condition may be provided by a high furnace pressure alarm and trip, intertrip of FD fans and fuel supply on loss of ID fans. You should study the arrangements on your boiler. It is essential that all protective devices on the boiler, including trips and alarms, be functionally tested at regular intervals to ensure that they do operate as required. You must be aware of the function of all protective devices and alarms on your particular boiler. Make sure that you know where all of the respective sensors are located, and also try to take part in the testing activities for protective systems. Now, we still have other areas to cover in relation to boiler operation, including control systems, emissions, and chemical control of boiler water. Now, this will have to wait for the next module. At this time, please switch off the tape and review this material in your workbook.